This recording is entitled Evaluating Limits Analytically. Also, I added algebraically, basically. We've seen in a previous video how to find them from looking at graphs, and then also from a table of values as it's approaching below and above that number. What's the y value doing? Now we're going to look at an algebraic technique, which is very useful when you can apply it. You can't apply it to every limit, but when you can apply it, especially limits that have answers that are sort of strange, that would be hard to interpret from either a graph or looking at a bunch of numbers, like what if the limit equaled 3 over 11 or something that would be hard to determine. Let's see. Let's look at some basic limits and their properties. If you replace x approaches c and f of x and you get f of c, that means that function is called continuous at c. And we're going to look at this more in the next section video. That's going to be something important that we're about to see here in just a minute anyway. So here are some properties that the limit of some value b equals b, as no matter what x is approaching. You can approach any value c. For example, the limit of 6 would equal 6 as x approaches 10. I could change that to x approaches 100. I could change it to infinity. I could change it to negative 50. It would not matter. Another way you could think of this, if you wanted to, you don't have to, but the b, you're taking the limit of b right here. The b is essentially your f of x. Well, if f of x equals b, that's just a horizontal line. So if you just envisioned a horizontal line, let's say at 6, if you're approaching from the left and the right on a horizontal line, it's going to be 6 everywhere on that line. So that's why it would not matter what you were approaching here. It would always be 6 because it's a flat line. The next one, limit of x as x approaches c, would just be c. So the limit of x as x approaches 5 would be 5. You can think of this as y equals line y equals x. So whatever x is approaching, y would equal that same thing. And then the last one says, assuming n is a positive integer, would not necessarily be true for negative integer. I'll give you a quick verbal example of that case, but x raised to the n as x approaches c would be c to the n. An example of why it must be a positive integer, let's suppose that n was negative 2, x raised to the negative 2, which of course is just 1 over x squared. Well, suppose that x was approaching 0. Well, if you put 0 into 1 over x squared, you're going to get an undefined value, so it's not going to exist. Well, we had some divide by zeros that did exist in the last section, but this one would not have a limit because we'll see it's a number that's not 0 over 0. Anyway, here are some properties of limits that you can read through these pretty easy. So it's telling you if the limit of f of x as x approaches c equals L, and limit of g of x as x approaches c is k. Here's some scalar multiple. If you multiply your function value by some b, that would just multiply the result of the limit by that same b. Plus or minus of two limit of a sum or difference would just be the sum or difference of their particular limit values. The limit of a product would be a product of the two limit values. The limit of a quotient would be the two values divided by each other, the L and the K. And of course, provided the K could not equal 0, you couldn't have division that way. You could divide by 0. And then if you raise it to the nth power, it would be L to the nth. And once again, n must be a positive integer, so you don't run into the divide by 0. Or here's another case of the 1/2. So like x approaches c equal negative 4, if you do that to the 1/2, negative 4 to the 1/2 does not exist because the square root of negative 4 is undefined. Now, this next example, we're going to see a lot quicker way to do this here shortly, but this is just sort of showing all the properties. So the first thing you can do is you can split that up into 3 limits. Be a much easier way to do this, though. But let me show you this real quick. Split it into 3 limits, and then you can bring the 3 out as a coefficient, and then you can bring the 2 out here, and then you put the 3 in right there for the x. So you have 3 times 3 to the 4th minus 2 times 3 squared, and then the limit of 5 would just be 5. The limit of a constant is always constant, and that ends up being 230 would be the result of that. Okay. Now, the process for evaluating limits analytically goes as follows. The first thing you want to do with any function is plug in your value c as x approaching c. Plug it into your function. If you get a result that's a real number, then that means if f of c is defined, that means that's what the limit's going to equal. Like I was intentionally, all those problems I was doing in the last section, they were designed not to work that way, so you can get a better appreciation for how limits are different than function values by definition, but they can't equal each other. So that's the first thing you do, is plug the number in. If you get an answer, then that's the answer. Like, for example, this limit of x approaches 2 of 3x squared minus 5x plus 7, you just put 2 in there. So it'd be 9. And that goes back up to this problem, which, yes, the better way to do this problem would have just been to plug 3 in for the x, and that would have been, that's essentially what happened anyway. So you would not need to go through all that business of splitting it up into 3 pieces. I just kind of drew a graph, meaning you'd have a nice, smooth, continuous graph, 3x squared minus, although it wouldn't look like that this graph though, because this equation is a parabola, but still. Anytime you have the limit of f of x as x approaches c, and when it equals f of c, you've got a continuous value right there, no gap, no holes, nothing like that. So, all right, so how about this one? X goes to 4 of x squared plus 16 over x plus 4. And you put in 4, and you would get 32 over 8, which would equal 4. Now this is where you make sure you have the algebra skills to realize that x squared plus 16 does not factor. I've seen that mistake made. I've seen people call this x plus 4 times x plus 4, then cancel one of the x plus 4s. That is not true. Now how about this next one? You plug in 5. Remember, it's okay to have 0 in the numerator as long as you don't have 0 in the denominator. That's when you run into trouble. But 0 in the numerator is no problem, because 0 divided by 28 is just 0. So that limit would actually equal 0. So that's the first thing. You plug it in, you get an answer, you're done. That means the limit will equal the function value, the problem's over. Now, here's where it gets kind of interesting, which it was, sort of in the last section. When you have 0 over 0, different things can happen here when you have 0 over 0. Well, one thing that won't happen is the function won't exist limit-wise. The limit may or may not exist. It just depends on how it turns out here. So look at the process. Now, this will not work every time, and I'll show you some examples of that. But if it's kind of an equation that has some, polynomials and this sort of thing like this, what you want to look for is see if you can factor and cancel and then reevaluate f of c. And this goes back to that very, very first one we did, where I showed the table of values and all that kind of stuff. Well, so you see, you plug 2 in there, you get 0 over 0. So as I said in a previous video, though, from a function standpoint, you can't do this canceling, but you can from a limit standpoint. But, obviously f of 2 is still undefined right here, no doubt. I'm going to make that shine a little brighter there. But you can factor and cancel, and then you plug the 2 in, you get 2 plus 2 equals 4, and which is exactly what we got using graphical and numerical methods. Graphical and numerical methods from the previous section video. So 4, obviously, that would be the best way to apply this one. Now, sometimes you can't do that, so then that's when you would strongly consider reverting back to graphical or numerical methods. Now, sometimes trig ones can be kind of interesting because you may have to conjugate things and do some manipulations to trig functions or other weird stuff. But here's a couple that you just kind of, this would you'd use either graphically or a table of values, which we've already done. I'm not sure if we did sine of x over x, but that's a pretty famous one we'll talk about here in a minute. But we did cosine of x minus 1 over x. And that was one that we saw was approaching 0. So you would just go back and use that technique. There really isn't anything else. You could multiply top and bottom by cosine of x plus 1 and play with it that way, and you would get, let's see, that would give you a negative sine squared on top, but you'd still have 0 on bottom. So yeah, that wouldn't do you much good. So this one, so then you want to revert back to the other, it's like, so there's 3 techniques now. There's algebraically, graphically, numerically. Same thing here. You can see this one approaches 1 from both sides. There's a hole I kind of highlighted you might not be able to see. So notice I'm not saying that 0 divided by 0 equals 1. I'm not saying that. I'm just showing that when you plug 0 in, you'll get 0 over 0, but the limit turns out being 1. Just want to clarify that. Now, if you plug your c in there and you get some number that's non-zero divided by 0, I think this did not stretch out far enough. There we go. Non-zero divided by 0, you're going to get limit does not exist. Now, you can use, if they're approaching the same infinity, you can make arguments for that, but I don't worry about that. I just stick with DNE as a notation. Now, something we learn in the next section after this one for one-sided limits, we'll look at whether it's going to negative infinity or infinity. But for now, we'll just use the notation of does not exist for this type of situation. So let's look at some examples. How about this one? X squared plus 9 over x minus 3. X squared plus 9 does not factor. So don't make that mistake. X squared minus 9 certainly would. So plug in 3, you get 18 over 0. So that's certainly non-zero over 0. That does not exist. For the next one, plug in 0. You get cos of 0, you get 1 plus 1, you get 2 over 0, so we would say that one does not exist. Now, here's an interesting little theorem that, I bring this up from time to time. I've even used it in Cal 2 for a couple of things. Well, let's take a look at this. I might have there might be a quiz question that relates to this. In fact, okay, let's see. Let's see. Now, so this says, if you know for sure that an f of x function is between an h of x and a g of x, and you know for sure that the limit of h of x as x approaches c equals some value L, and the limit of g of x as x approaches c equals that same L, if both the outside functions equal L, then the inside function would have to also equal L, because if it's squeezed between those two. So I just kind of put a little graph here that this might not be the best example, but it's not bad. You see that, so f of x being the red line, the horizontal line, it's always between the g and the h. So, and you see the g and the h are the same limit. But actually, this could be like a wavy line, as long as it didn't go outside, but then we'll have to straighten out. Anyway, long as it stays between those two, it would have to be the same. If g of x and h of x are approaching the same value as 0, f of x would have to be approaching that same value at 0. As you can see here, I brought up number 1 on quiz 2. I didn't remember if I'd put this in there, this hint in there. I meant to, but sure enough, it looks like I did, that it's telling you to use the squeeze theorem. So that means all you have to do is evaluate the outside limits, x cubed and x, as x approaches 0. And then this is just telling you that x is between negative 1 and 1. But all that matters is that x is approaching 0, so whatever the outside limits equal, the inside function would have to be the same thing. So if you plug in 0 into the two outside values, you'll be able to see real easily what that would be. All right. That takes care of the squeeze theorem. Now, here's two special trig limits, which we've now we dealt with cosine of x minus 1 earlier over x and came out to be 0. But these, so you could always, if you didn't remember what these were, you could always develop these graphically or numerically. You could generate these if you needed to. Like, for example, sine of x over x, x approaches 0 equals 1. I didn't do a whole table of values, but I just put in negative 0.001, nothing you'd see, and positive 0.001. I picked two values close to 0 on both sides of 0, and look how close they are to 1. So you can see that limit would definitely equal 1. And in fact, that's also true for this relationship I wrote right here of ax and ax. So that means limit as x goes to 0 of sine of 6x over 6x would equal 1. And then if you flip it over, it also equals 1, x over sine of x. Now this one, the 1 minus cos of x, is actually the same as cos of x minus 1, because just imagine if you pulled out a negative out of that numerator. Well, this one, we've already seen, ours was, I'm just showing you why that one was also 0, given the one we've already done, that we know is 0, if this one is 0. Defined as 0, and you could also work this all the way around. So those functions are negatives of each other. So if one limit is 0, the other one then is the negative of that limit. So therefore, negative 0, of course, is just 0. So that's why it's 1 minus cos x in this case. That's because it's equal 0. Or cos of x minus 1 is also over x is also 0. All right, but if you flip that one over, you get dne. Another reason that that's true is because if this was 1 and then you flip it over, 1 over 1 will be 1. But if this limit's 0, as soon as you flip it over, 1 over 0 does not exist. Now here's a picture of this graph right here, x over 1 minus cos of x. So you see as it approaches 0, it's going two completely different directions. So it's going opposite directions, so it definitely does not exist graphically. All right. Now you got to be careful with sometimes using these properties, because notice that in both cases in these special limits, x is approaching 0. So you don't want to train yourself to think anytime you see sine of x over x that the limit's going to be 1. It is if x goes to 0, but what if x is approaching some other value? In this case, pi over 2. So in this case, if it's not 0, you just plug in pi over 2. So you get sine of pi over 2 over pi over 2, 1 over pi over 2, which would then flip over and be 2 over pi. Now this one, as x approaches pi, so once again, x is not approaching 0, so you have to plug the value pi in there. So you have 1 minus cos of pi over pi, and just by coincidence, that one also happens to equal 2 over pi. Because cosine of pi is negative 1, so you have 1 minus a minus 1. Now, I guess this one didn't have to go through it. It does equal 2 over 7, but the actual formal way to do this would be using this idea right here in green. Is that what I did is I put a 2 with that x and then put another 2 in there, because that way if I have a 2 over 2, it's still 1, right? You're still multiplying by 1. But then in that case, by putting a 2x here, I can clearly say by definition that equals 1. And then I'm left with a 1 over 7 and a 2, and multiply together to be 2 over 7. But now that you see how this works, you don't have to really worry about doing all that. So to make that more interesting, kind of problem I would like to put on a test or something is sort of do something a little bit different like this. Now you got to be careful. If you have a larger powers on top than bottom. But what you want to do here, like this one, sine squared of 4x over 81x squared. So what I did is I split this up, sine squared as being sine of 4x, sine of 4x. I pulled out the 81, so I left it as x over x. Now I needed a 4 here, so it would match that property like right here. I needed, if that's a 4x, I needed this a 4x. And then match a 4x here. And so if I put 2 4's in the denominator, I have to also put 2 4's in the numerator to balance it out. Once I put those 4's in there, I can cross those out because those just become 1s now. So you're multiplying by 1, so those go away. So you're left with the 81 on bottom. You have 2 4's on top, and that would end up being 16 over 81. But you have to be careful that, let's say if it was a sine cubed and you were left with another sine on top. Actually, if you had a sine on top by itself and you put 0, you'd get 0, and it would turn the whole thing into 0. So just kind of break it up into individual sines and individual x's, into individual pieces, and just see what's left. They may not always match up perfectly like this. You may have an extra x. If you end up with an extra x on bottom, you're going to get divided by 0, and you'll get does not exist. If you have an extra sign on top, you'll get 0 as the answer. All right. This one's real easy. This is just kind of, now we're looking at just a variety of problems here. Plug in 3, you'll get square root of 9 over 5, so it's 3/5. Now this one, you put 5, you get 0 over 0. And x squared minus 25 certainly factors. But then if you look at this, x minus 5, x plus 5, at first glance you might think nothing cancels. But actually, these are opposites. Opposites meaning that they're completely opposite in sign. 5, negative xx. Complete opposites means it'll cancel to a -1. So it's kind of sneaky there. They look like they don't cancel, but they really do. It's -1 over x plus 5. And then when you do that, it leaves a -1. Then you reinsert the 5. After you've factored and canceled, you reinsert the 5. And 5 plus 5 will be 10. So you have negative, so the answer will be -1 over 10. About limit absolute value of x over 2. I'm sorry, limit as x goes to 2 of the absolute value of x minus 2 over x minus 2. That's definitely 0 over 0. I used graphing here. You could have used a table of values. But with the absolute value, there is no factor and cancel or anything like that. You have to revert back to either numerical or graphing. Graphing's good enough because you can see as x approaches 2, they're not even close to approaching each other. They're not even, that's just like we did absolute value of x over x in the last section. They're 1 one way, -1 the other. Does not exist. Let's look at this next one. X approaches 2. You factor this. Now, I'll give you a little hint when you have these sort of problems. Whatever x is approaching, you're expecting a common factor of so if that's 2, you're expecting x minus 2 to be you're looking for something that's going to make it be 0, top and bottom. So let's suppose x was approaching -3. Then that means you're expecting your factors to be x plus 3. So that you don't have to remember that. That's not that critical because you can always factor it. But it would save, that way you'd know automatically that, when you factor this, one of them is going to be x minus 2. But that's okay. Factor it normal. The x minus 2's cancel. You reinsert the 2. You get 2 plus 4 over 2 plus 1. You get 6 over 3. That equals 2. Now, these can be a little tricky, but they're not that bad. Just got to apply a little basic algebra. Conjugating a radical. That's how you'll handle it anytime you see something like this. Conjugating basically turns it into something where you have the difference of two squares. So we have this problem. Limit as x approaches 3 of the square root of x plus 1 minus 2 over x minus 3. If you insert 3 in there, you will see it's 0 over 0, because always remember, just because you see a radical doesn't mean you have to do this. The key is when you plug the number in and you get 0 over 0, that's when you'll do this. Remember, if you get a real number answer, you're done. Or if you get something like 3 over 0, you're also done. But in that case, you're done by getting does not exist. This one's when you get the 0 over 0 that you're looking to apply this conjugating the radical technique. All right. So conjugate means you just change the sign between the two. So it'll be the square root of x plus 1 plus 2. Now, let me give you a little hint here. You are going to multiply the top one out. The bottom one, do not multiply it out. Leave it, you want it to be just like this. You'll see why here in a minute. Don't FOIL, don't do anything to the part that you're not conjugating. You have to show it as multiplication, but don't multiply it. Now, if you multiply this one out, you're going to get those radicals cancel. And then the square root of x plus 1 times x plus 1 will be x plus 1. Two square roots cancel. And negative 2 times positive 2 is negative 4. And you have x plus 1 minus 4 is x minus 3. Now you can see why you don't want to multiply those two things on the bottom. Because now it enables us to cancel the x minus 3's real easily. Leaves a 1 on top. And then you put in the 3, and you'll end up with 1/4. And you can see I put this one in maple just to show you. Now this next one, we put the radical on the bottom just to show you, it could be at either place. But you plug in 5, you're going to get 0 over 0. That's the key. That's how we know we're going to conjugate. So you have 3 plus the square root of x plus 4, top and bottom, because whatever you're doing, you're conjugating wherever the radical is, whether it's top or bottom, then you're multiplying the other top or bottom by the same thing. In this case, we don't multiply out the top. We just leave it like that, and we FOIL out the bottom, but really you don't have to FOIL because we specifically know because of this right up here that we're only using the outside two terms. So 3 times 3 is 9. The two radicals multiply together, and that cancels the radical. But keep in mind, all of that is after this minus sign, so always be careful about your negatives. So 9 minus x plus 4 is 9 minus x minus 4, and you get 5 minus x. And we just saw this a few minutes ago. So it might look like, hey, nothing cancels there, but remember, these are opposites here. So x minus 5 and 5 minus x, that will cancel and leave a negative 1. So it does cancel, but leaves a negative. Then you plug in 5 over here to the right, and you'll get 3 plus 3, which is 6. Negative 1 times 6 is negative 6. And Maple happens to say it's negative 6, so that's always good. Always trust Maple. All right, let's look at this weird one right here. You put 0 in here, you're going to get 1 minus 1, which is 0 over 0, so that checks out. We're going to do a trig conjugate here thing. Here we're going to do cosine of x plus 1 over cosine of x plus 1. Now you can always try, graphing these, stuff like that, but it's these negative 6 you probably could have seen from a graph, but what if it would have been a weird answer, like going back to, and we'll do fractions here in a minute, but that 1/9 right there we saw from another video. Would have been hard to get 1/9 that way. 1/4 might have been tricky also. Graphically, it would have been really tricky. Numerically, maybe. Anyway. So multiply them, get cosine squared minus 1. That turns out being negative sine squared because actually 1 minus cos squared is sine squared. You see what I did right here? You bring the 1 over, bring that, makes that negative sine squared. So, and then you don't distribute on the bottom. Leave it just represented as multiplication. So you leave it like that. Turns into negative sine squared. Now you still have 0 over 0. You can't just plug 0 in there because of this. And I split that up as, you see there's two signs on top, two x's on bottom, so I split it up as sine of x over x, sine of x over x. I'll put the negative over here. The negative could have gone anywhere. But we saw those earlier, those limits equal 1. So they go away. And then you're just left with this last part. You insert 0, cos of 0 plus 1 of 0 is 1, 1 plus 1 is 2, so you get negative 1/2. Complex fractions. You can go, this one, you don't have to really conjugate or anything. You just you need to get it simplified down into one working fraction. That's the best way to deal with it. Conjugates aren't necessary. Now what I did here is I have two denominators, an x plus 4 and a 4. Therefore, I know a common multiple between them will be 4 times x plus 4. So I went with that technique, top and bottom. So in other words, I wanted to break those. I only want one big fraction right there in the middle. I'm trying to get rid of those little fractions, which I'm successfully doing. So if you take 4 times x plus 4, that'll cancel the x plus 4s, and you'll be left with 4. You do it again to the 1/4 term, the 4s will cancel, and then you're left with the negative still here, though, and then x plus 4. Now, don't get silly algebraically and do anything bad like this. You cannot cancel those x plus 4s. You cannot do it, because that's minus right there. That's a common algebra mistake. Like if you had, let's see, a minus b over b. Those b's don't cancel at all. So that's one key thing about calculus is you don't want to make algebra mistakes. Even if you know what you're doing, you need to also know algebra to be able to do these successfully. So now I simplify that numerator. The 4s will end up canceling. I'll be left with negative x. That's good. Because that way now, since everything's multiplied down here, I can cancel those x's because it's multiplied. That will leave a negative 1 on top. That x goes away. Reinsert the 0. You'll get 4 times 4, which is 16, negative 1 over 16. Yeah, that would have really been a tough problem to find the exact answer numerically or graphically. This was the one from the last section that turns out being 1/9. So this one I used 3 times x plus 1 because those are the two denominators. So I multiply, the x plus 1s will cancel, it leaves me 3x. Here the 3's will cancel, so it leaves me 2 times x plus 1. So that'll basically be 3x minus 2x minus 2. So 3x minus 2x is 1x, and then minus 2 right there. So and then on the bottom, you see you leave it, just don't multiply the bottom part out. Leave it as individual pieces multiplied together because we always want to cancel something. Makes it easier. X minus 2 is now canceled. Perfect. Leaves a 1. Then you put in the 2, you get 3 times 3, so you get 1/9. Okay, here's a trig one we're using theta. So we're looking for basically, anytime that we can get this case it's theta, so I'll say, so we get sine of theta over theta, especially because we're going to 0. Anytime we have a sine of theta over theta, we know that we're going to have a 1. So this one's pretty simple. You rewrite tan as sine over cosine. The cosines cancel, and you have sine of theta over theta as theta goes to 0. By the limit definition, you get 0. 1. 1 is the answer for that one. That was the same property of sine of x over x. So the answer is 1. So that's why I didn't show anything there, just because we're using our previous result. How about this one? Cos of x over theta as theta goes to 0. You plug in theta, you get 1 over 0. You stop right there. Anytime you get non-zero over 0, the answer will be does not exist. So we are finished with that one. Tan squared of x over x. So that's sine squared over cos squared. I'm always looking to pair up sine x's and x wherever I can find them. So there's a sine x over x, which means as x goes to, especially when it goes to 0, obviously, but that makes it a 1. So it leaves me a sine here and a cosine squared, and that is 0 because you don't have 0 on bottom. You have 1. Cosine of 0 is 1, therefore cosine squared is 1. So you have 0 over 1, so you can now call that 0. 1 times 0, that's going to be 0. Maple says it's 0. Everybody says it's 0. That's wonderful. So I guess I left this one here to see if anybody wanted to give that one a whirl to see what would happen. And I went ahead and put the answer there if you wanted to try it. You'll get 1 for that answer instead of 0. How about this one? We've got, now this one, it's trig, but it also sort of kind of turns into a complex fraction because you kind of want to get the sine tan broken down into the sine of a cosine. So I want to get rid of that little individual fraction first of all. Then I can worry if I need to conjugate or anything like that. And so I multiply top and bottom by cosine to get rid of that cosine right there. So it's going to leave me cosine minus sine on top. Not sure how I end up. Oh, I ended up with 2 of those. And so I have cosine of sine of x on top, nothing on the bottom other than the cosine of x going in there with it. So this is where we would recognize that those are opposites. Therefore, oh, I guess the cancellation lines were off. Now I can see what's going on. That's why it looked weird. There should have been a like this. There we go. Makes it -1. Now it's -1 over cos of x. So pi over 4, put pi over 4 in there. Cosine of pi over 4 is the square root of 2 over 2. So -1 over the square root of 2 over 2 flips over, makes it -2 divided by square root of 2, which would then simplify into the negative square root of 2. Now this next one, I probably wouldn't put this on an exam, but I thought it was kind of interesting because it kind of goes back to an old algebra technique called synthetic division. You could certainly look that up on YouTube if you want to see a video of how it's done. But you see, though, this one, you could actually do this one, though, with a table of values. But my point being, this one actually, the x to the 5th minus 32 factors. And it cancels that x minus 2, and you're left with all this. And then you plug 2 in there, and you get 80. But you can see it's going to be 80 from over here, also if you did it that way. But I'll do this real quick here. So you have to put in, see, we have x to the 5th, and you got to put in a 0 for every missing power all the way down. So all you have is an x to the 5th, and then you have the minus 32. And if this is x minus 2, you use positive 2. If that had been x plus 2, I'd use negative 2. That's what enables us to add for synthetic division. So I'll do this real quick, and you could look this up if you wanted to, but I don't think you're going to need to do this for exam purposes or anything. I just thought this problem was kind of interesting to look at. So you bring the first number straight down is 1. 2 times 1 is 2. Add makes 2. 2 times 2 is 4. Add 0 and 4 is 4. 2 times 4 is 8. Add down, get 8. 2 times 8 is 16. Add down, get 16. 2 times 16, 32. Add down, you get 0. That 0 is the remainder. So anytime, obviously, if you have a remainder of 0, that means when you divide it, that means it goes into it without, perfectly. So the bottom row of these are coefficients, and so if you started with x to the 5th, that means your first one on the bottom will be x to the 4th. So it's x to the fourth plus 2x cubed plus 4x squared plus 8x plus 16. So that's where this comes from, right here. That bottom row right there. You put 2 in there, you get exactly 80. But this would have worked also right there too. So, all right. Well, I believe that concludes this video for finding limits analytically, aka algebraically.